So vectors are something that when we first introduced to them, they seem that it's almost it doesn't seem like they're that big a deal. But it turns out, if you go further in math, the vectors really they get used for things that you really can't imagine that you would use them for. They are extremely powerful, and they get applied in lots of different situations. So what we're going to do today is have an introduction, try to get our heads around what the idea of what a vector is. Tomorrow we'll make some connections between vectors and what we've done with trigonometry. And then on Monday today we're going to learn some basic operations with vectors, adding and subtracting. On Monday we'll talk about one way that we multiply them. Towards the end of the year, we'll talk about vectors again, vectors in 3 dimensions, and we'll talk about another way to multiply vectors. And when we learn that other way of multiplying vectors, we'll also learn another way to find the area of a triangle. That has to do with vectors. So, the idea of a vector is that it's something that has magnitude and direction. It's not enough to just say we have $25. We want to say we're traveling 25 miles an hour and we're going that direction. Because 25 miles an hour that direction is different than 25 miles an hour that direction. So we want to keep track of the direction. So a vector is a quantity that has magnitude and direction. Some examples of vectors, the velocity is a vector. You need to know how fast we're going and what direction. Forces, any kind of force that you would talk about in physics class, you're going to describe with a vector. Electromagnetism, gravity, any of those kinds of things are going to be described with vectors. And when you work with them in any kind of detail, you work with vectors. We can also think of position as a vector. In a lot of circumstances, it's convenient or it's nice. The math works out nicely to think of, instead of a point just on the coordinate, that the point is so far from the origin and in that direction. So that's another way that we can think of coordinates as vectors. All right, the idea of a vector is or what our book calls it is a directed line segment. So that's what your book will say. I think it's more convenient, just visually, to think of them as an arrow. So let's draw a vector here. And some of the terminology is going to be familiar, and we're going to take advantage of that familiarity as we move forward. So there's an arrow. We call the point where it starts, I'll call that P. This is the initial point. And the vector ends at some point, I'll call that Q. And that's the terminal point. So very similar to the way we talked about angles and our initial point and our terminal point. We could, when we label vectors in writing, we could call this vector V, and we use a little half arrow over the top to say it's a vector and not some other kind of thing. We could also call it V, or sometimes you label vectors with their initial point and their terminal point. You'd say vector PQ. We write the magnitude we write with double bars the magnitude of V, or we could write the magnitude of vector PQ. and the magnitude is the length. So the double bars are kind of like absolute value. We want to know how big it is. Absolute value tells us how big a number is. We don't care if it's positive or negative. The magnitude is kind of the same thing. We want to know how long it is. The magnitude, if we're talking about how fast you're going, the magnitude would be your speed, 25 miles an hour. And then we turn it into a vector by taking into account the direction. We find the length using the distance formula. And we'll do an example here in just a second. So there's the big picture. There's our idea of a vector. It's an arrow, points a certain direction. The length of the arrow tells us how big the force is, how fast we're going, how strong the wind is blowing, for example. Short arrow would be not very strong wind. A long arrow would be stronger wind. And sometimes you'll see maps, weather maps, that have arrows that show the winds. The length of the arrow represents the wind speed, and the direction they're pointing is the direction the wind is blowing. All right, vectors are equal or equivalent. If and only if they have the same magnitude and direction. So we compare vectors by deciding, are they the same length and are they pointing in the same direction? We don't care about where they're located. All that we're interested in is, do they have the same length? Do they have the same, are they going in the same direction? So 25 miles an hour that way is the same as saying 25 miles an hour that way. As long as we're talking about 25 miles an hour in the same direction, we're talking about the same velocity. Now, depending on where you start driving, you might end up at a different place, but you still have the same velocity. All right, so let's look at an example with some of these ideas. Questions? Questions so far? Yeah.
What's the distance formula?
We'll talk about that with the example. We'll do the distance formula in the example. All right, so we want to, let's let V, vector V is a vector from 0, 0 to 4, 5. And U is the vector from 2, 3 to 6, 8. We want to show that they're equivalent. So in this case, what the problem's asking us to do is compare magnitude and direction. So let's find the magnitude of each of these and see if they're the same, and let's figure out a way that we can tell what direction they're going. So the magnitude of V is the distance formula, square root x2 minus x1, so 4 minus 0 squared, plus y2 minus y1 squared. And this is going to be the square root of 16 plus 25 square root of 41. And the magnitude of u, square root of x2 minus x1, 6 minus 2, squared, plus y2 minus y1, 8 minus 3, squared, and we get the square root of 4 squared plus 5 squared, square root of 41 again. So they have the same magnitude. How are we going to figure out their direction? Yeah? Slope. The slope will tell us the direction, right? So let's look at the slope. The slope of v is y2 minus y1 over x2 minus x1 by fourths. And the slope of u is y2 minus y1, 8 minus 3 is 5, x2 minus x1, fourth. Same magnitudes, same slopes. So that tells us that u equals v, or v equals u. Now we'll talk about another way to write out a vector, and we'll talk about come up with a different way that's really equivalent to decide if vectors are the same. All right, so questions so far? Okay, let's talk about the component form of a vector. This is so component form is the form that you will, one of the two forms that you will see most often for a vector. All right, so I'm going to draw a set of axes here, and we're going to talk about a vector in standard position. So this is x, this is y, this is my origin, 0, 0, and I have some vector out here going to some point that I'm going to call v1, comma v2. So those are just the coordinates of that point. And then instead of x and y, I'm calling them v1, v2 because this is a vector. And this is vector v. When our vector has its initial point at the origin, we call this vector, we say the vector is in standard form. Just like an angle, when our angle, the initial side of the vector was at the, or sorry, the angle was at the origin, and our angle was from the positive x-axis. That angle was in standard position. This is in standard form. Sorry, standard, did I say position? Standard position. And in this case, we can say that the vector v, we use angle brackets, and we just use the coordinates v1, v2 to describe the vector. And what this is telling us is we go v1 units in the x direction and v2 units in the y direction to get from the initial point to the terminal point. We call this the x component, and we call v2 the y component. And when we write our vector like this, this is component form. And really what we're doing here is we're breaking this down. This drawing hopefully is familiar. we're breaking this down into a little right triangle. This side of the right triangle is V1, and this side of the right triangle is V2. So we're talking about how far we go in the x direction, how far we go in the y direction. And you might be able to visualize, now that we drew this little picture, how we might then start applying trigonometry to these vectors when we talk about them tomorrow. If we are not in standard position, so we just have our initial point at some point and our terminal point at some other point. So I'm going to say this point is x1, y1, and this is x2, y2 at the terminal point. I'm going to call this vector u. Well, what we're going to do here is exactly what we did with our vector in standard position. We're going to make a little triangle. Well, this side of the triangle is x2 minus x1. This side of the triangle is y2 minus y1. So we can say u in component form is x2 minus x1, comma, y2 minus y1. And that would be vector u in component form. And that tells us how far we go from this point in the x direction, and then how far we go in the y direction to get from here to here. And we would call this, again, the x component and the y component. So that would be the component form of a vector. Component form is very handy, because if our vector is in component form, if v is v1, v2 in component form, then the magnitude of v is the square root of v1 squared plus v2 squared. And what we're doing here is we're just using the Pythagorean theorem to find the length of a hypotenuse. The Pythagorean theorem and the distance formula are the same thing. And in component form, it's very easy to see if vectors are equivalent in component form. So I'm going to say u is in component form u1, u2, and v is v1, v2. U equals v if and only if u1 equals v1 and u2 equals v2. The components are equal. So if we look at our vectors in component form, we just compare the components to see if they're equal. All right, we good so far? Okay, I want to jump back to that first example we did, and we'll look at the component form. So we want to show, again, u is the vector from 0, 0 to 4, 5. Same problem that we did before. And v is the vector from 2, 3 2, 6, 8. Show that U equals V. Well, I'm going to write U and V in component form. U in component form is x2 minus x1, y2 minus y1. It's just going to be the vector 4, 5. And U would be a vector in standard position. V is the vector x2 minus x1, 6 minus 2, 8 minus 3. They're the same vector. In component form, we see that the components are equal. So that tells us that U equals V. So we don't have to do, when we put our vectors in component form, we don't have to do nearly as much work. Component form compresses all of that information about the direction and the magnitude all into one nice little set of brackets. That's one thing that's beneficial with vectors, is that the notation is so compact. This has all the information about the magnitude and direction all together. All right, let's look at another example. It's similar, but we want to find the component form and magnitude of the vector V from 2, negative 4 to 5, 7. Well, component form is easy. We just subtract. The way that I think of component form, and let me go back here really quickly. I forgot to make a note here. The way I think of this is terminal minus initial. To find our component form, we just take the components, the terminal points minus the initial point. So just a way to think about doing that. All right, so terminal minus initial, 5 minus 2 is 3. 7 minus negative 4 is 11. So in component form, vector V would be the vector 3, 11. What that tells us is to go from 2, negative 4, 5, 7. I go 3 units in the x direction and 11 units in the y direction. The magnitude of V is just going to be the square root of 3 squared plus 11 squared. Component form, we've already done the subtraction, so we don't need to subtract the 2. And this comes out to be 9 plus 121, square root of 130. And that would be fine for an answer, square root of 130. Okay, we good so far? When we do these magnitudes, there was a class that I took a couple years ago where for different kinds of things, you find the lengths of them in different ways. And the different ways that you find the lengths of them, we'd indicate by the number of bars around. So we'd have some things that had 2 bars around them, some things that had 3 bars around them, some things that had 4 bars around them. And you're doing all these operations with them, multiplying them together, dividing. I ended up with lots of vertical bars written all over the page. All right, let's talk about some operations. Last thing we need to talk about today, operations with vectors. We want to learn how to do some arithmetic. Vector arithmetic. All right, so for this part, we're going to say that U is our vector u1 comma u2, and v is the vector v1 v2, and k is a real number, just a real number. When we're dealing with vectors, we call real numbers scalars. So we want to learn how these things interact with each other. So to add vectors, u plus v, that's just going to be u1 plus v1, comma, u2 plus v2. We add the components. And we call this vector addition. When we add vectors, we call it vector addition. And if we multiply a vector by a scalar, k times u is k, we can also write it u1, u2 in component form. That's k u1, comma, k u2. We call this scalar multiplication. We'll talk about vector multiplication on Friday. On Monday. One way that we do vector multiplication. We can do vector multiplication in two ways. We'll talk about one way on Monday. The other way has to wait until we talk about vectors in 3 dimensions. What multiplying by a scalar does is this multiplies the magnitude by k. So it makes the vector, if k is 5, it makes the vector 5 times longer. Doesn't change the direction, just makes it 5 times longer. 10 times longer, whatever, half as long. If k is negative, so it's less than 0, multiplying by a negative points the vector in the opposite direction. So if we had, I'll draw just a visual here. If this is vector u, whoops, I wanted a vector there. If that's vector u, then negative u is going to be a vector exactly the same length, but just in the opposite direction. So putting a negative in front just changes the direction. We can also subtract vectors, and we can think of subtraction as adding a negative. So u minus v is the same as u plus negative v. And in component form, that's going to be u1 minus v1, comma, u2 minus v2. We subtract the components. And this is still part of vector addition. We can think of it as adding a negative. Good morning. All right, questions there? All right, the last thing I want to talk about is what this addition and subtraction means graphically. So visually, what are we doing when we're adding and subtracting vectors? So graphically, we add vectors head to tail. So what we mean by that, let me draw a set of axes here, and we'll put some vectors on there. If this is vector u, and we want to add vector v, we put vector v, so this is the head of the vector, this is the tail. We would put vector v there. And then we would connect, make this one red. We would connect them like that. And that vector that we made there would be u plus v. Another way that you might visualize this, and sometimes they do this in your physics class, is you can draw a parallelogram. So I would put vector u here and vector v here. And then you can think of u plus v as a diagonal of that parallelogram. So each side of the parallelogram here is v, each of these sides is u. And the u plus v is the diagonal of the parallelogram. And we subtract vectors tail to tail. So same setup, we're going to have our axes here. And if we want to subtract u and v, so there's u, and I'm going to put these two tail to tail this time, like so. And this is vector u, the green one, and vector v is a blue one. Make my arrow a little nicer. And if we want u minus v, what I'm thinking about to do u minus v is, well, I'm going to connect these two, the heads of these two vectors, but I need to get the direction correct. So I'm going to think of minus v as turning that one around. So I'm going to visualize, or you can draw it in if you like. This would be minus v. Turns it around the opposite direction. So the red one is minus v. So u minus v, I'm going to put the red one and the green one together. Well, with the red one and the green one, I'm starting here at the tail of this one. I go here, and I end up here. So u minus v would be this vector that goes that direction. So I'm thinking of adding u plus minus v. V minus u, if I switch them around, v minus u would go the other direction. We don't have to do a lot with vectors graphically, but it's good to be able to visualize them a little bit and what you're doing with them graphically. All right, questions? Kind of a lot of sort of new information. In your book, in print, vectors, they don't use the arrows. In print, vectors are in bold. So they'll use boldface type to denote vectors. But in writing, we do the arrows. So let me think. Did I get everything? I think we're okay. The other stuff we'll talk about on Friday. All right. Generally, with this assignment, because there's not a lot, it's not complicated, but because it's relatively new, students, a lot of times students will have questions. So please make sure you ask questions.